Okay, let's move on to another topic. Okay, so I have something interesting to hear for you. All right, it's not about AIDS. It's about AIDS, but it's interesting. It's a drug. Oh, anyway, just listen. I don't know what I'm saying. Okay, so AIDS, you guys familiar with it? So acquired immunodeficiency syndrome is caused by a virus called HIV, human immunodeficiency virus. Right. All right. One thing you need to know. I'm not sure you're familiar with how a virus works. How does it kill people? If you've been following with the COVID virus, HIV virus do this. Have similar, actually have the same mechanism of how to kill people, right? So all viruses don't have what's it called, the mechanism of replicating itself, right? So they can make a baby, basically. That's what I'm saying. So it needs that mechanism of a normal cell from a host to be able to replicate. Right, and survive. So here's what happened. All right, so HIV just contains a DNA. That's a genetic material, right? But it can't replicate it. So it needs a normal cell. Let's say in our body. The target of HIV is a white blood cell. We call CD4 plus cell. That's a white blood cell. All right. So they will use the receptor right here, bind to the receptor on the white blood cell, and to open the gate and transfer the genetic material to the white blood cell. And the white blood cell have the ability to replicate itself, which means this new white blood cell become a virus, and you make another baby viruses. Okay, and which means that over time the number of white blood cell will be lower and lower and lower, right? As the virus kind of bind to more and more white blood cell and replicate. Okay. Now, I'm sure you guys know that white blood cell act as the defense for our body, right? And we need to have a certain level we call certain count of a white blood cell so we can survive, right? The normal white blood cell level is about 800 to 1200 counts. Okay, that's CD4 lymphocyte. That's a white blood cell, right? If you have the number of white blood cell or count lower than 800, you're gonna get some of the herpes, malaria, and this one is a fungal infection, candida. I don't know what that is, right? So that's when your white blood cell count is lower than 800. If your white blood cell count is lower than 200, you start having pneumonia. Right? Lower than 100 counts, you start having a brain infection. Right? Lower than 100, so 75, 50, you're gonna get all the brain tumor and stuff right here. Tumor, herpes virus, and cytomegalovirus. I don't know what that is, but you die. Basically, what I want to say is the virus HIV doesn't kill us, but all these other diseases will kill us when we have lower number or lower count of white blood cells. Okay. And of course, human race try to fight back by making an anti-HIV agent, right? We have all this stuff right here, okay? But one thing that the biggest problem in terms of making medicine for the viruses, here's the thing: the HIV resistance, right? The drug resistance. This one I took it from a website. This is the bacteria, but I mean it's the same concept there. Let's say we have a virus come to your body, they replicate, right? Some of them replicate differently. Yeah, they replicate. So all this virus, the genetic inside the DNA is prone to mutation. Some of them can mutate. Right? So let's say 100 of them, maybe one or two of them look similar, but inside a little bit different. When you treat this guy with the medicine, most of them die, but maybe only one or two survive. But this one or two can function just like a normal viruses. Okay, so it will just bind the white blood cell and replicate. Now, but this time they replicate the one that can resist to drug. So we have a problem here. We can't kill this guy with the same drug. All right, and so a common and popular anti-HIV agent is called boviride. I don't know how to say it, right? It looks something like that, right? What does it do? It can bind to the receptor right here, or somewhere here, not all of it, but somewhere on the virus, block it from binding to the white blood cell. So basically, this guy binds to the virus, and the virus cannot bind to the white blood cell. Basically, that's how it works. All right, and there's a conformation. It's called look like a butterfly, so they call butterfly conformation bind to the virus. But here's the thing, though, those viruses that have mutated. That those viruses get rid of that binding pocket, which means this drug cannot bind to the virus, and that virus just like say, oh, this drug can't do anything to us. We just kill more people, right? So we make a different. So for that purpose, we make a new drug that can do this. Take a look at this. We have a new another drug called R1000943 ITU, whatever this name is, right? This guy is another type of anti-HIV agent and do the same thing, bind to the surface of the virus, block it from binding to the white blood cell. But when the virus get rid of that pocket, this guy cannot bind to that pocket. But this what this drug can do. It can rotate. Take a look right here. We have carbon-carbon single bond. Carbon-carbon single bond can rotate, right? From this conformation to something that look like a horseshoe. They call a horseshoe in a conformation, and bind to a different site on the virus right there. This is the virus surface of the virus. Yep. This conformation can bind to this pocket, block the virus from binding to the white blood cell. All right. So my point is, carbon carbon single bond can rotate, and we're gonna talk about this in a bit. All right, something I have to clear it up real quick. So conformer or conformer is either way. You can call it either way, like a transformer. All right, so conformer is different from constitutional isomer. Constitutional isomer is the same molecular formula but different connectivity. All right, but conformers are the same compound, but they rotate. Carbon-carbon single bond rotate, right? Go back right here. These two are the same compound but different conformers. They are not isomer. They're not constitutional isomer. They're the same compound, same molecular formula, same connectivity, right? But the carbon-carbon single bond can rotate. They are at a different conformer. Okay, so they're different conformer. The same compound we call conformers of 1, 2, 3, 4, 5, 6, 7 heptane. These conformers of heptane. These are constitutional isomer of heptane. All right, let's go to the next video, something a bit more interesting right here.